This is Jundan. I'm glad to present NIID-Net Adapting Surface Normal Knowledge for Intrinsic Image Decomposition in Indoor Scenes. This work was done when I was at Zhejiang University and the Science-Time Joint Lab of 3D Vision with Zhaoyang Huang, Yijin, Xiaowei Zhou, Guofeng Zhang, and Hujun. Intrinsic image decomposition, which is simply called IID, means to estimate multiple physical characteristics from natural photos. Typically, researchers aim at estimating a reflectance image and a shading image from a single input. In the IID task, shading estimation is to recover real lighting effects of a scene. So estimated shading is commonly used for photorealistic image editing, which can be applied in augmented reality applications. The decomposition equation is shown here. Many works, including ours, have focus on immersion scenes. Under this assumption, the input image can be simply reconstructed by a channel-wise multiplication of its reflectance and shading. However, the decomposition equation is under constraint. To release ambiguities in the decomposition process, extra priors or information are required. In recent years, promising progress of IID has been achieved by automatically learning priors from training data. But at present, there are no methods or devices to annotate dense intrinsic image labels in real scenes. Lack of training data is another problem hindering the development of IID. In order to release the two problems I mentioned above, we propose NIID-Net. This is a learning-based framework that improves IID by making use of available surface normal datasets. Inspired by previous works, we take surface normal as our extra information. Moreover, we propose two novel ways to integrate learned surface normal knowledge into IID. In the following slides, I will give a brief introduction to our NIID-Net. So, this is an overview of our proposed NIID-Net. We focus on shading estimation, so we omit the reflectance branch here. The NIID-Net consists of a normal estimation module and an IID-Net. It takes a single image as input, predicts a surface normal map via the normal estimation module, and predicts intrinsic images via the IID-Net. What is special is that the branch of shading estimation integrates surface normal knowledge. The fundamental component of the NIID-Net is the normal estimation module. It is singled out and trained to capture geometry features and predict surface normals. After pre-training the normal estimation module, we design an encoder-to-encoder block to share geometry features. This block is called normal feature adapter. We use 3 adapters to propagate scene geometry features to the IID-Net, so that the IID-Net can focus on learning complicated lighting conditions with the support of geometry priors. The normal feature adapter is designed like this. It extracts and encodes useful features by an up-projection block, and then it uses concatenate and convolutional layers to fuse features. Besides feature sharing, surface normal information is further incorporated via rendering. The main challenge in shading reconstruction is how to model the spatially varying lighting conditions in indoor environments. In our work, we propose to represent it by pixel-wise integrated lighting. The integrated lighting is derived from the Lambert rendering equation. In Lambert scenes, shading is the summation of the contribution by each incident light. The shading caused by each light is the dot product of the surface normal and the lighting vector. We rewrite this rendering equation in this form. The final shading of the illuminated point can be reconstructed by a vector that encodes its nearby lighting environment. The vector A is the integrity of lighting, so we call it integrated lighting. In order to represent spatially varying lighting indoors, we propose to predict a map of pixel-wise integrated lighting vectors. In our work, shading is reconstructed by predicted surface normals and predicted integrated lighting. Compared with pixel-wise spherical harmonics lighting models proposed by Zhou, pixel-wise integrated lighting vectors are lightweight and easier to train. Summarily, our NIID-Net learns knowledge from the available surface normal datasets and adapts this knowledge for IID via normal feature adapters and rendering. Normal estimation is trained on the real-world datasets, while shading estimation is trained on the synthetic CGI dataset. The network details and loss functions are presented in our paper. As for experiments, we evaluate our method both quantitatively and qualitatively. Here, we show some quantitative results on the real-world test sets. As for reflectance, a smaller number is better, and our NIID-Net achieves the fourth best result among all these methods. But if compared with the models only trained on the synthetic datasets, that is the CGI and the SunCG, our NIID-Net achieves the best. As for shading, a higher number is better, and our NIID-Net achieves the best performance in shading estimation among all these methods. Note that the IID-Net part of our framework does not require training on the real-world datasets, but it can achieve the best performance in shading on the real-world test sets while incorporating knowledge from surface normal. We also conduct visual comparisons. We compare our shading image with Li's result and Zhou's result. Li's model directly predicts shading from a single input image, while Zhou's model first predicts pixel-wise spherical harmonics lighting models and then reconstructs shading. We and Zhou both want to take surface normal as extra information, but we make use of it in different ways. Here, blue rectangles show that our shading results have the least texture residuals. Orange rectangles show that our method recovers the sharpest highlights and the sharpest geometry contours. Besides, Li's shading image is of low contrast. Also, we visually compare these methods by surface recoloring application. We recolor some surfaces in a real scene. For each method, the new surfaces are rendered by multiplying the target reflectance with its estimated shading. The red arrows show that our method recovers the darkest shadows on the floor, the bed, and the wall. Besides, as shown by the blue rectangle, our method has less erroneous texture residuals in the shading image. In Glauch's result, some residual textures are shifted into the estimated shading. We believe that shading estimated by our method is of the best quality. We show that if we use shading learned by our network, we can also conduct editing of illumination-varying image sequences. We show two of them here. Each sequence will be displayed twice, once at a faster speed and another time at a lower speed. The left image is the original image, and the right image is edited with estimated shading. For more information, you can reach me through the email shown here, and the source code for our method is available online. Thank you very much.